Okay. Any questions? All right. So continuing. Oops. Okay. Further. All right. So here's the code. If you remember last time, we talked about how do we actually handle multiple programs? How do we handle running various different, programs, right? And what I told you is that, a good thing to do. Here's the code, guys. Those of you who are late. What I said was what we need to do is kind of a dynamic kind of way of handling different programs, right? And then we introduced the concept of page tables, right? So we said that essentially every program has to be broken down into pages, and then we kind of scatter these into my main memory. And the first problem that we faced was these pages could be anywhere in the main memory. So what we do? What we should do is using some form of tracking mechanism for finding out where are these different tables. And that was the idea of what we call page tables. The second thing that we talked about was this thing, this distinction between what we call virtual address and physical address. The reason that we have virtual addresses, every program thinks that they have access to the entire memory, right? The program at the software level has no idea of what is the size of the memory, what's the difference between disk, what's the difference between cache. These are all transparent to the actual programmer, okay? So that's why we let the programmer to deal with addresses without really being worried about these kind of differences. And we call that virtual address because they're not the same as what's really happening underneath in the hardware. And then we kind of deal with this virtual to physical address translation internally inside the hardware, right? In order to do that, we do this translation, this address translation, which essentially all it does is takes a virtual table number and then kind of go inside one table and kind of looking up at where this address is mapped to, right? So it's essentially looking at this address, goes into this table, and then find this page number. And we also talked about this additional part of the address called page offset. And if you remember, I told you that I still need my address, my memory to be byte addressable. As a result, if I'm kind of bunching them together into a one block, which is, for example, it's a 4 kilobytes of page, I need to somehow still be able to find my byte within that one block, one page. So if, for example, I'm using 4 kilobytes of pages, there are 2 to the power of 12 different, bytes in that. So as a result, I need 12 bits in order to be able to address the blocks, the bytes within that page, okay? And since that part can be the same for virtual address and physical address, in order to save some time, we don't need to necessarily translate this. This part can just directly be used from the virtual and physical. So essentially, the kind of byte offset within a page, there is the same thing for virtual address and physical address. As long as we kind of keep track of like that 4 kilobytes the page size granularity, both on the virtual side and on the physical side, then we are okay with this part, right? This was kind of the architecture that they are using, right? So there's like literally a table where it has index for every single virtual address possible. And within that, we kind of stores the actual page number. And then we start talking about where do we store the page table. And that was kind of like the last thing that last time we did. We talked about the page table itself is a big, storage unit because as actually we can calculate for example, for a 20-bit page virtual page size, we need about 4 megabytes of data per process. And if you have like 10 different processes or 20 different processes, which is kind of the normal number in most of our systems, we're talking about tens of megabytes just for storing this mapping, not the data itself, just the mapping, in order to kind of like, know where we have stored the actual address. And then another kind of like, artifact of this is that now our kind of memory accesses really are 2 accesses. The first access is for figuring out the physical address, and the second access is the actual like finding and reading the content, right? So let's talk about these two, and let's see how we can kind of optimize our design based on this kind of 2 criteria. First of all, let's talk about how we can compress the page tables, but because it seems that 4 megabytes per process seems to be a very large number, okay? So let's talk about how do we compress page tables. The way that we're going to do this is this key inside, this key idea that we're going to use what we call hierarchical page tables, okay? So we can basically say that page table itself, there could be a page table for that page table, there could be another page table for that page table. In other words, we're kind of creating a hierarchy of these page tables so that we don't need to store everything in one giant table. There are tables that's kind of like, there are one table that's kind of, point to another table, points to another table, and points to another table. And I'm going to describe how this can actually help us, why this is useful. First of all, let's give you the idea of how the hierarchical page table works. And then I'm going to describe how this can actually save space. So essentially, the way that we're going to do this hierarchical page table is we're going to break down the address. Remember, previously I told you this is my virtual page number. And there was just one table that we kind of indexed through and then find my physical address there. There was just one table. Now I'm saying that, okay, let's say instead of having one level, kind of just one level of page table, let's have 2 levels of page table. As a result, I'm kind of like breaking down my address into 2 pieces, P1 and P2. Let's say, for example, for now, I decide to have equal size for level 1 and level 2. So what I'm going to do is that I'm going to say that I'm going to have a table, this first level table, level page, level 1 page table that you see on the right side. And I'm going to use the kind of P1 address set in order to kind of address through this table, okay? And then what I'm storing in that table is now the pointer to the next level table, okay? So what I'm going to store here is the content. Let's say, for example, the content is that red rectangle. That red rectangle is basically pointing to the base of the next level of the table. And then from there, we're going to basically use the second portion of the address, this P2, and use that as an offset to this base in order to find this second rectangle, red rectangle. And that's where we actually store the actual address, okay, the actual physical address. Okay, so this is basically where we're going to say that, okay, this is the actual page that we are looking at. And then this last offset is essentially, the byte offset that's we basically use from this offset here. Okay, so what is happening here again? What used to be just one level of abstraction, one level of indirection, is now 2 levels of indirection. And then the trick that I'm using is that in the first level table, I'm not storing the actual physical address. What I'm storing is the pointers to the second level table, okay? So every content in this level 1 page table is essentially the pointer to the base of these second level tables, okay? And in the second level tables is actually where I'm storing the actual physical address, okay? So this is kind of the idea of hierarchical page tables, okay? So to kind of see why this is, so first of all, this idea of like we go to the first level and then go to the next level and the next level, we call this page table walking, okay? We're kind of like, it's as if that we are walking through levels of page, okay? So in order to understand how does this help to kind of like save space, Well, this kind of like baseline implementation actually, in fact, doesn't help us to save space. In fact, if you calculate how much space do I need for this, I need this first level table that requires, like, if these are 10 bits number and each one kind of like storing a 32-bit byte, 32-bit data, I need 1,000 of this, and each one is 32. So this is just the storage area for the first level. And then I'm going to have 1,000 of these, and then in each one is actually it's 1,000 times so. So each of these level 4 tables are actually again 1,000 times 4, and I have 1,000 of these tables because I have 1,000 entries in little level 1, and then I have each one is 4K kilobytes of size. And then actually, if you do the math, you see that this is actually significantly larger than 4 megabytes of data. So it's actually worse. What we are doing right now is worse. But what is really happening is that we are banking on this idea that virtual memory is actually quite sparse. If I kind of go back here, yeah. If I go back here, I told you that within the software, we assume that we have access to the entire memory, right? But in reality, my physical memory is actually even smaller than what I have per program. So why does actually even work? Why, sorry. Why this, why notability doesn't work? That's one question. The second question is why this even work? Like why we have smaller storage area, but we think that we have all the storage area and we actually have multiple programs. How come that we are kind of mapping a bigger thing to a smaller thing? The reason for this is that although that we assume that we have access to everything, in reality, we only use this very, very sparsely. So although we kind of assign a big area for my data, assign a big area for my code, assign a very large space for my heap and stack and so on, every program, the real utilization of this is maybe somewhere between, let's say, 10% or 20% of the entire program memory. That's why we can actually, fit lots of applications together, because in reality, although we technically have access to the entire program memory, we only use 10 or 20% of this because we only maybe have a few lines of code, maybe we store only a few kilobytes of data and so on and so forth, okay? So as a result, I'm only accessing things that I'm really using. I'm not gonna assign page tables to things that I'm not using, okay? Which means that this basic idea that this could help us is the fact that virtual memory is very, very sparse, which means that not all the pages in the virtual domain is really assigned to a real physical address, okay? So how does that help? So assume, for example, that, within this first, level of my page table, there are lots of these addresses that are not even assigned to any real page table, okay? So all these yellow parts is kind of removed from the second level. So the effective, space that I'm really storing is only those that I'm really using. So this one and this one, in other words, I really like storing 2 levels of hierarchical page tables in the next level, okay? So then if we actually do the math, we'll see that, this size is actually significantly lower than what we expect it to be, okay? Because we only have a few lines that, in the first layer that is really assigned to the second level. And then if we eliminate those second level tables, we are actually saving a lot of space, okay? So if we actually, so this is just an approximation, by the way, this is not like a real number. But what's really happening is with this trick of using true level addressing, especially if you pay attention, I'm using the higher level bits because this is usually where things are very, very sparse. What is going to happen is that in many, many cases, these are not really assigned to any real kind of virtual page tables. And as a result, I don't really need to store anything at the second level. And as a result, I don't really need to spend the entire my entire space for storing it. I only assign page table to things that I'm actually use. Okay. And then of course, if my program needs more data and needs to store more things, I can assign a new page table and then I can create this. But on average, this is going to be very sparse. As a result, I'm storing very, very little data. You got a question? Okay. Any questions? Yeah. Yeah, the 1K, so the question is how do we calculate the size? So this 1K times 4B is for the first level, okay? Because, for example, I have 10 bit of data, so I have 2 to the power or 1K rows. Each row storing 32 bits data, right? So 4 bytes. And then for the second level, I need to know how many of these tables I have and what is the size of each of those tables. So the size of each of those tables is 1K times 4 bytes, so still 4 kilobytes per table. But now the question is how many of those tables do I need? So what I'm saying is that what's really happening is that the number of tables I need shrinks significantly. So for example, it becomes 1/4 or 1/8 or so on and so forth. So that's where you're gonna get, your big saving is basically each line that you kind of eliminating from this table, you are saving 4 kilobytes of data because each one is pointing to one giant table and then you are eliminating. Does that make sense? No. So the question is, why are we still storing 4 bytes here? So remember, these are still addresses. So still we are storing this inside my memory. So still my addresses are all 32-bit data, okay? So I still need to know where is the beginning of this page table, and that's the 32-bit data, okay? So what is the real content that I'm saving within each of these is just a 32-bit data, which is the actual memory address. They're all, so the content that they're storing are all physical, okay? I'm using virtual address to index them, okay? So your virtual address is just used for indexing them, but the actual content is really the address that this is stored in the memory. Yeah.
So we're basically dynamically allocating that allocation is in by
Yes, the question is, since we are kind of dynamically allocating more pages, then of course we need to update the page tables. Who is handling that? And the answer is is the operating system. So the page table is continuously changing as you're adding and removing things from your programs.
Wait, so is it allocating the actual the second level page tables?
Yes. Yeah. So allocating here means just we need to kind of, so think about this is that this one level is it has the indices and it has this valid bits, right? So it's like, the way that we kind of allocating arrays in our programs with like new and free or malloc and exactly the same thing. So we kind of saying, oh, okay, this is now a valid pointer, or it's not a valid pointer, so I can store other things. Oh, so you mean like part of the data in one page goes to another? So page tables themselves. So the question is, if you want to kind of save things, do we kind of move things around? Yes and no. So first of all, your pages should be continuous 4 kilobytes of address. And that part you cannot change. So you cannot like store 4 bytes from here and 4 bytes from somewhere else. They have to be continuous 4 kilobytes of data. But what you can do is that you can, for example, allocate a bunch of things together for, let's say, if you remember, I told you about like the data segments and code segments. Yeah, so usually the operating system kind of allocate them in continuous, chunks so that they actually map into lower level bits so that we can actually store, like, save. But these are kind of compression techniques that the operating system does. Yeah. Yeah.
Sorry, I'm not sure if you, but I thought the paging was handled by the memory management unit.
Mhm.
How does the operating system interface with the MM? If the OS is responsible for managing the hierarchical page table, then How does that influence the NO?
So the question is like if you have like a memory management unit that is implemented in hardware, and then we have the operating system, which is the software, how does things work? So part of these things are implemented hard-coded in hardware, and part of it is actually done by like just software. Most of these kind of allocating page table, removing page table, all those things is actually done by software in the operating system, okay? So MMU, think about it as what we call hardware support. So for example, it provides the storage, it provides some functionality, but most of these things, since they're very complex, it's better to do it in the software. That's why you'll have thousands of lines of code in your Linux kernel, right? Because you're doing all these things basically. Yes. The question is that does that mean the memory becomes not 3 cycles, but yeah, if you walk, then every level is 1 memory access. That's a very good observation, actually. So page walking now is more expensive because what used to be 2 now is 3, or actually modern systems has multiple levels. There's not just 2, there's like 4 or 6 or 8 or so on. So yes, it could be 8. You know, if you get unlucky, it might be multiple. All right, so kind of like summarizing what is hierarchical page tables. So we need page table for address translation, but page tables are very, very large, and we need to store them inside the memory. So we need the idea of hierarchical page table, and basically what it does is leveraging this idea of sparsity in order to compress this storage. Okay, that's how we actually kind of benefit from this. But now, as exactly you said, now I'm basically telling you that every axis is now multiple axes, right? And for example, if you remember, I told you that in L1 I really need very, very fast hit times. I need to really quickly within 1 cycle go and grab the data. Now I'm telling you that whatever we did in the cache doesn't matter because I need 2, 3 axes just to find that address, and then inside the cache I can find it. So it's kind of counterintuitive because we spend a lot of time optimizing the cache, but now we need to go to the main memory and bring the address itself. So I mean, why bother even to have a cache if you need to have multiple accesses to just get the address, right? So let's actually talk about. Of course, this is not we are doing. So let's see what we actually do. So the idea that we are actually doing is that since this what we call address translation needs like a memory lookup, what we can do is that we can have a cache of this kind of like address translation. Okay. So we can actually cache the recent address translations. And instead of going to the page table and then do the page walking and then finding the address and then going to the cache and bring it, how about we store the recent, address, virtual to physical address translations within our cache, so that the first thing that we do is actually see if we have that translation. If we have it, then boom, we can actually go to the cache and bring the data up, right, back to the CPU. Okay, so we're kind of using the cache or some form of caching to remember what we have translated, so that then we can access the actual cache faster. Okay, and this is what we call translation look-ahead buffers, or TLBs. So you can think about TLBs as kind of something that sits here. So basically, I told you that the CPU first needs address translation, and we call that memory management unit. Within the memory management unit, the very first thing that we do is that we are querying this kind of small cache, small buffer called TLB. If the data is in the TLB, we already have our physical address, because TLB is essentially, think about this, is that, so what we are getting here is the virtual address. If the virtual address to physical address translation is already here, then we have the physical address at this point. So essentially, you can just continue as before. We can just go to the L1 cache and and look for it. If it's not, go to L2, L3, and so on and so forth. The only problem is when the data is not in the TLB, and in that case, this would be what we call a TLB miss, or what we call a page fault. Oh, sorry, a TLB miss, not a page fault. It's a TLB miss. So we need to go to the page table and bring that data, find that physical address, bring that bring that data, that physical address, and then we can go to the cache. So of course, this path here is significantly slower than this path, because this path requires kind of at least two memory accesses, okay? But this path is just looking up very quickly a page table which is within the same access time of an L1 cache, as I'm going to show you later. So what's really become critical here is that you really want to have a very high hit rate TLB, right? Because if you can't manage to do a good job on in storing recent translation there, then you're gonna have a very fast system, right? So what would be the hit time of your L1 now? So your hit time of your L1 now becomes the hit time of your TLB plus the hit time of your L1. Best case scenario, if your translation is actually already stored in the TLB, then best case scenario is that your data is stored in L1. So the faster that you can recover this data from the memory hierarchy is that it's inside the translation is inside TLB and the data is inside L1. So at best you are TTLB plus TL1, right? That's your hit time. That's your new updated hit time. Previously, this was not here because we are only assuming that we had physical addresses. But if you have virtual to physical translation, you need to consider both the TLB time and L1 time. Is that clear? Any questions here? Yeah. Yes. So the question is TLB just converted from, yeah, literally just virtual to physical. That's all. Yeah. No. So the question is, does TLB stores the hierarchical? No, it's literally the physical page, like virtual page number to the physical page number. But of course, the TLB cannot store everything, right? So maybe it's like a 16 entry. So only the latest 16 virtual to physical address translation is stored there. Yeah.
So if page table is stored in
Mm-hmm.
data has
Mm-hmm.
So how does it know where to go when
So the question is, if the page table itself is stored inside the memory, where do we know even where the page table is? So that's again where the operating system comes into the play. So remember I told you that we reserve some of the space for the operating system. So operating system knows where stuff is. Okay, so when you actually need the address translation, it requires the operating system to kind of give that address, and then we go to the memory. So we know where my page table is stored per process. And then these are basically, think about it as there are special registers that stores the base of each of those page tables. So per process, we have that base. So everything else is just the offset to that base. What's that? Yeah, exactly. Yeah. So I'm asking, the question here is that what is the fastest hit time for my memory hierarchy? Okay. And the fastest hit time that we have for memory hierarchy is when my data is in L1, right? So previously I told you that the data is in L1, we call that hit time of L1, right? I'm just showing it as T of L1. And I told you that this is within one cycle usually, right? What I'm saying now is that because of this virtual address to physical address translation, the best case scenario is that the address is inside my TLB, so I already stored that, but I still need to pay the penalty of this looking up the TLB. So my hit time of L1 is now TTLB plus TL1. And then of course my hit time of L2 would be TTLB plus TL1 plus TL2 and so on, so, right? Yeah, so you store the physical address in, so you in TLB, you store the physical address. The outcome of your TLB, as I'm showing here, is the physical address. And then this physical address is the address that we used to use in our caches. Let me see, there was a question there. No, yeah.
Yeah, you might have answered this already, but is there a reason we don't use TLB for L2 and L3?
So the question is why we are not using TLB for L2 and L3. Remember, we just need to translate the virtual to physical ones, okay? So addresses in CPU is virtual. After MMU, everything is physical, okay? Once it's physical, then you don't need to keep translating, right? So you have your physical address and that's it.
So the TLB would handle it for all levels.
Yeah. So at this point, all I have is physical addresses. It's the same thing that we said before. If you remember, actually, when we were discussing caches, we never talked about virtual addresses. We always talk about physical address. The reason is this, that there is a step before it that actually does a translation, and that's my MMU. So the question is, if the address inside the TLB, are we guaranteed that the data is inside the cache? No. It just means that this is a recent virtual to physical address translation. It might be in the main memory, it might be in L3, it might be in L2, it might be evicted. We don't know. So there is no correlation. It's likely because it means that since we recently translated, it's probably we brought it to the cache, but it's not guaranteed. So this is kind of how your TLB looks like. So your TLB is literally all it does is storing a tag, okay? And then this tag is just the entire virtual page number. This is you can think about it as a fully associative cache, okay? TLB is usually implemented as a fully associative cache. So we store this page number, virtual page number as the tag, and we store the physical page number as the content, as the data. So when the data comes, when the virtual address comes, we compare this VPN with this tag. If it's a match, then we have our PPN. We get our PPN, and then of course the offset just gets right into the address. If it's not in the cache, we call it a TLB miss. And if it's a TLB miss, then we need to go to the page table. So we need to do the actual page table walk, okay? And once we do and gets the actual physical address, then of course what we need to do is that we need to refill this TLB with this new address, right? So same as like the way that we did it for the cache. If it's not in the cache, we go to the main memory, we bring the data, but we also install that data into the cache because the next time we're going to use it. So how do we design the TLB? So TLB is usually somewhere between 32 to 128 entries. Most of the time it's a fully associative cache. So one big thing about TLB is that it's used spatial locality significantly because we are storing 4 kilobytes mapping into one entry. So it's very, very likely that consecutive memory accesses all match into one page, right? Because we're talking about 4 kilobytes of data. So it's very likely that we kind of keep using the same page over and over again. That's why we call it actually a page, right? So TLB actually experiencing a lot of hits because if your data is actually spatial, is using spatial locality, you're going to see a lot of TLB hits. If we use larger TLBs in more sophisticated processors, then we can actually use 4-way or 8-way cis associatives. Sometimes actually you might even kind of do the same trick that we are doing with caches. So you can actually have multi-layer TLBs. So you don't need to necessarily have just one TLB. You can have like L1 TLB and L2 TLB. And then you usually have either a random or FIFO replacement policy for for TLBs. The reason that you don't do LRU is that you won't see spatial locality that much within pages, because one page to the next page is already very, very distant from each other. That's why it doesn't really worth it to have some form of an LRU or something, because the reuse of pages are significantly less than reuse of cache lines, okay? Because these are much bigger. As a result, we typically do some form of FIFO or random for TLB. And then there is this important concept called TLB reach. And then that's basically the biggest amount of data, continuous data, that we can store in the TLB. How do we actually calculate that? So since I told you that, for example, each entry is 4 kilobytes, if I, for example, have a 64 entry page table, and assuming that I'm storing consecutive pages, then 4 times 64, that means that I can store 256 kilobytes of consecutive data in my TLB. We call it TLB reach. The reason that this is an important thing is that most of my programs are actually continuous. So if the data that I really need to load into my memory is less than this TLB reach, then I essentially have almost 100% TLB hit rate, right? So that's really why this TLB reach is important. So as I said, TLB miss will cause what we call an exception that I'm actually going to talk about in this in the rest of this lecture. And then the handling of misses happens by the operating system. So everything is software. You had a question? Yeah. The question is, why do we use random or FIFO replacement policy? The reason is that if you remember, the reason that we were using LRU was locality, right? So we said that, oh, if I read this line, it's very likely that I'm going to read it again, right? In pages, this is unlikely. Why? Because now we're talking about 4 kilobytes of data. So we are talking about locality of pages. And what I'm saying is that locality of pages is less likely, okay? Because if you're done with one page, it's very unlikely to come back to that page. That's why, I mean, it's still possible, but what I'm saying is that usually doesn't work. Yeah. Random is kind of equally performing as an LRU, for example. But it's just a minor thing. Yeah, you can use LRU. All right. But to answer your question, Benson, you can actually use the MMU to handle TLB misses. So you can actually hard code this in the hardware if you want to. Okay. So now we are talking about these kind of things. So the only thing that we haven't talked about is the disk, okay? And if you remember, I told you that we have memory like DRAM, and you have disk. And both of them, we call it main memory or memory, but in reality, these are two separate things. The reason that they are very different is that their latencies are significantly different, okay? So the disk is, this significantly larger storage, but significantly slower, okay? So what we need to do is that in order to efficiently use this, we need to use the same kind of memory hierarchy idea that we have. We try to kind of create this illusion that whenever we are accessing my main memory, I'm accessing my DRAM and not my disk. But in reality, sometimes I'm accessing my DRAM, sometimes I'm accessing my disk, okay? So the utilization is important here. So in order to kind of like, manage the data between my DRAM, which is the upper level, and my disk, which was the lower level, is that I'm going to keep the page formatting that I introduced earlier. So I'm still going to think that things are stored in my memory or my disk in page by page format. But I'm going to use basically this idea that I'm going to swap pages from my disk to the memory, okay? So what I'm going to do is that if data is needed, okay, I'm going to put those pages in my DRAM. If data is not in the DRAM, then I need to go to my disk, bring that page and put it into the DRAM. And we call this kind of operation swapping, because you always kind of get rid of an existing page in the DRAM and you swap it with what you have in your disk. So you always kind of do this swapping operation in order to kind of read the data from the disk. And then whatever I say for this, you can actually create the same analogy between cache and main memory. For cache, we said that we evict the data, we put it to the main memory, or if it's not in the cache, we go to the main memory and bring it to the cache. Same story happens with DRAM and disk. If the data is not in the DRAM, we go to the disk and bring it to the DRAM. If data is in the DRAM, then we don't need to do, go to the main memory and so on, right? So things are very similar, but generally, as I said, we think that we have M storage bits, which is the combination of disk and the main and the DRAM. If we put most of things in DRAM, first of all, DRAM size significantly lower than the disk size, so C is much smaller than M, and C is the capacity of the DRAM, and M is the M is the capacity of DRAM plus disk. So what we do is that if I have M pages, which is all pages that I have in my system, if I put C of them into my DRAM, the rest would be in the disk. Of course, this means that not always accessing to the DRAM will be a hit. Some of the pages are in DRAM, some of the pages are on the disk. If the pages are not in the DRAM, we call it a page fault, which means that the page that we are looking at is not in the DRAM, but it's of course in the disk. The reason that this is a big deal is that the access to the DRAM significantly faster than the access to the main to the disk. That's why the page fault creates lots of delays, right? But again, this happens very, very rarely. The reason for this is that my DRAM is big enough for most cases, so I rarely need to actually go to my disk. Okay. So how do we actually have a page fault? Why we have a page fault? If you remember in the page table, I told you that for every single instance of VPN, we have an entry in my page table, right? But also, if you remember, I told you that my my DRAM is usually much smaller than my address space. So for example, this is 2 to the power of 28, 2 to the power of 20, something like, the number of rows that I have is not actually 2 to the power of 32, which is the entire address space that I have, right? And also I have multiple programs. So actually, in fact, this is even larger than this I need, okay? But since I'm saying that, okay, every single virtual address needs an entry in my page table, but in reality, I'm not storing everything in my DRAM. In order to distinguish what is stored in the DRAM and what is stored in the disk, I'm going to use this valid bit here in my page table. And if this valid bit is equal to 1, it means that I brought that page into my DRAM, so it exists in my DRAM. If this valid bit is equal to 0, it means that I never read that page from my disk and never brought it to my DRAM. So that's where we're going to call this a page fault. It's actually, I don't have that data inside my DRAM. I need to go and bring it from the disk, okay? So that's the kind of like, this is the way that we distinguish what is stored in the DRAM and what is stored in the disk, okay? So how do we actually design this kind of like demand paging? In other words, how do we decide what to put in the DRAM and what to put in the disk? And by the way, we call this demand paging because based on the demand, we put things into the DRAM. Otherwise, we store it in the disk. This demand paging is very, very similar to the cache. So, you want to put things that you're recently using in the DRAM. You want to maximize your spatial locality, temporal locality, and all those things. So I'm not going to repeat those things, but the same stories is actually happening exactly here. So same kind of replacement policy, et cetera, actually happening here. And then whenever we need to evict a page from the DRAM to the disk, we call this a swap. Okay, we don't call it an evict, we call it a swap. And then what happens is that you just kind of move it around. Another thing that you can do is that you can have what we call large page size in DRAM. So you can actually, the same idea of blocking that I said in the cache, you can have the same thing in DRAMs as well. You can bunch, big page, pages together and call what we call a large page, which is usually in order of multiple of kilobytes instead of just 4 kilobytes. So, I mean, bottom line, the one I want to say for this slide is all the techniques that we learn in cache design directly applicable when we are talking about DRAM and pages. But the granularity changes. In caches, we talk about bytes and blocks. In DRAM and disk, we are talking about pages and super pages. Okay, so the granularity changes. Since the granularity changes, my delays changes and my kind of locality behavior changes, but the principles stays the same. Okay, any questions? Cool. And then the important thing here is that all of these things for between the DRAM and the disk is handled by the operating system. So essentially everything is handled by software. The reason that we are doing it and we are not really doing it in hardware is that, accessing this is already very, very slow. Okay, since this is very, very slow, you don't need to speed this up with using hardware. You actually can use software, which is much cheaper, which is much easier to implement, which is much easier to kind of update and so on. So all these kind of LRU replacement policies, whether or not, I need to kind of evict this or that, you don't need bits in the hardware for tracking this. Everything happens in software. Okay, so the operating system is the one that's making all these decisions. The reason that we didn't do this for cache is that we needed things to be responsible within cycles, 1 cycle, 2 cycle. So software cannot really give you that speed up, that performance. Okay, so that's the difference. So the question is the number of pages changes in the DRAM depending on what applications we are using. Yes, so if you're actually using different applications, the operating system might decide to bring the relevant pages to the DRAM. As a result, we need to kick something out. We need to swap the pages, right? No. So you always, the DRAM is at full capacity. Like you store as much as you can in the DRAM. That's why we call it swap, right? So you always kind of swap. Of course, at the beginning when you boot your system up, there's nothing valid in your DRAM, right? So there will be some time for your DRAM to fill, but very quickly your DRAM fill, and after that you just keep swapping between your disk and your that's why when you're actually, for example, working on a particular application, you see that it's very responsive. But then when you're opening your, MATLAB for the first time, it takes a lot of time for it to boot up, like to initialize. But then you kind of play with your MATLAB and it works great, right? That's why the first time that your data was in this, it needs to bring it to the DRAM, lots of page faults. But then once you're kind of interacting with your software, you see that it's actually very responsive because now everything is in your caches and in your memory. Yeah. Yes. So the question is, if not page table, pages. So the granularity between DRAM and disk is in page size. Okay. So you evict a page and then you replace it with another page. 4 kilobytes. Yeah, but again, 4 kilobytes is just an implementation. You can have 8 kilobytes, you can have bigger. Most of the modern systems have what we call super pages, which is combination of pages. So we don't really evict one 4 kilobytes. We usually evict the entire big page, large pages we call. Yeah. Yes, so the question is, if the page table is too large, where do we store it? Yeah, you can store the lower levels in disk, right? But again, remember that if you're storing things in this, you're significantly hurting your performance, right? So usually the page table, you want to store it in your DRAM so that you can quickly recover it. All right, so kind of to updating this picture, remember I told you here is my virtual address. The virtual address comes to my MMU. The first thing that we're gonna check is TLB. If the address translation is there, then we actually go directly to my cache. I don't need to be worried about anything else. Otherwise, if the translation is not in TLB, I need to go to my page table. But in page table, now two things might happen. If the address is in the page table, if the valid bit is equal to 1, it means that I have it either in my main memory or my cache. So I continue. If the data is not even in the page table, it means that we have a page fault, which means that the data is actually in the disk. So there needs to be, first, I need to bring that data to my main memory and then continue whatever I was doing before, right? So basically very, very slow path here, because this means that I need to go all the way to the disk for accessing this data, versus this path here on the left side means that I can just quickly go to L1. So that's where kind of things, you see a significant change in the access time of your memory based on which path you're actually taking. And that's where the beauty of memory hierarchy comes into play. Because basically what we are saying is that if, for example, 99% of the time I go to this path, and only 1% of the time I go to this path, on average, I'm seeing the latency of this path, which is 1 cycle. But in reality, I have access to all things that I want. So I still can access my disk. But if I design my system such that most of the time I go through my L1 through the TLB, then I have a very, very fast system. Okay, that's the entire kind of idea of what we call about what we say memory hierarchy. Okay. So yeah, just a recap of page tables. I think we talked about this. I want to talk about one final optimization before we move on, and that's this kind of hit time. This hit time that we have. Yeah, question. The question is that if we have a TLB hit, does it guarantee that the data will be in L1? No. Actually, I think someone else asked this question as well. If you have the TLB, if your data is inside the TLB, it means that you have recently translate this, okay? But it doesn't guarantee where this, it doesn't show where this data is. The data could be in your main memory, could be in L3, and could be L2, or could be in L1. The only thing that it guarantees is one of these levels. It's not in the disk. That's the only thing that it guarantees. But it's likely that it's in L1 because you have recently translated this. Very likely it is in the L1, but it's not guaranteed. Okay, so I told you that my hit time, right, is now T of TLB plus T of L1. In other words, I'm telling you that access to the TLB and my L1 is serialized. So TLB is kind of in my critical path, right? And if you remember, I told you that my hit time is very, very important for us, right? Because we want to have this within 1 cycle. So now the question is there any way that we can parallelize or eliminate this TLB translation, at least for L1, okay? So this is kind of the optimization that we are looking at. So the first question is, can we access L1 before TLB? And do you think this is actually possible or not? Any suggestions? Can we access L1 before TLB? Why not? Yeah. But how? Because what is the fundamental problem that prevents us of doing this? The fundamental problem is your addresses before TLB are virtual addresses. Your addresses is stored in L1 or physical addresses. So I'm basically saying that can I use virtual addresses to access physical addresses? And of course, the answer seems to be no, right? So I cannot use virtual addresses to store L1, physical addresses. Why? Because what's the problem actually? Why can I cannot just store virtual addresses in my L1 and just access that? Anybody can say why we have this problem? Yeah. Yeah, so two programs can have the same virtual address because we never, prevent programs of not having same virtual addresses. I told you that each program thinks that they have access to the entire program memory, so they never bother to kind of share with other programs which addresses they're using. They always think that they have everything, okay? So we're gonna have this problem called aliasing, which means that there are program 1 and program 2 that they're gonna use the exactly same virtual address, okay? For example, I don't know, virtual address equal to 100, because they think that they have all the addresses. So now address 100 comes. How do you know whether this is from processor 1 or processor 2? How do you know which one you have even stored, right? So this problem is what we call aliasing, because virtual addresses can alias, can overlap each other's, but physical addresses are unique. So that's why I need physical addresses, okay? So what we can do in order to fix this, an optimization that we can do is that maybe we can design our system such that I can in parallel access TLB and L1. Maybe I can do some things in L1 before knowing the actual physical address. So what is that? So this is the idea of what we call virtually indexed physically tagged cache, okay? VIPT we call it. So the idea of VIPT or virtually indexed physically tagged is a very clever idea. So basically this is what is happening. So this is my virtual address, right? So virtual address has two parts. It has the VPN and it has the page offset, right? And if you remember, I told you that this part does not need translation. So no translation is needed for the page offset. So the key idea is that maybe I can use this page offset part for indexing my cache. The advantage of this is that now I can actually go inside my cache and grab the line that I want, okay? So basically what I'm going to do is that I'm going to say that as long as my block offset plus index, these are the two parts of my cache, as long as this block offset and index fits into my page offset, what I can do is that I can go inside my L1 physical address cache and at least pick the line that I want to check, okay? I'm going to go and pick that line, and then what I'm going to do is that simultaneously, in parallel, I'm going to also look up my TLB with the VPN and see if I actually have the translation for VPN. If I do, I have the physical address here. So I have the physical page number here. And now I can compare the physical page number with the tag. And then if it's a hit, then boom, I have my data ready, right? So let me repeat this one more time. So basically what I'm doing is that I take my virtual address. I already know that it's divided between page offset that does not require address translation and virtual page number that does require address translation. This part, I put it into TLB and then try to find the physical page the physical page number. At the same time, I'm using the page offset and using the index that is embedded in this page offset to access the index that I want from the cache. And then I basically bring that row. And then what I'm going to do is that once I'm bringing this row, hopefully this translation also happens. So at this moment, I can just basically compare the tag and physical page numbers. And if the answer is yes, I have my data. Question? The question is, does this imply that your first L1 cache has to be direct map? So if this is actually a set associative, though, instead of bringing 1, you bring 4, for example, and then in parallel you compare it with 4. Okay, so you just compare tags. What I'm saying is that you find the row, bring the row, and then you do in parallel check the tags. Any questions? So how does this help? Because now I'm hiding the latency of my TLB by doing these things too in parallel. Okay, so if I actually look into my hit time, now the hit time is the maximum of the TTLB and TL1. And since this TLB is usually very small, in fact, we are going back to my TL1. Okay, so I'm going back to what I had before. Okay, so as long as I'm designing my TLB such that this search is much faster than this search, then I'm really not adding anything to my hit time. I'm still back to my L1 hit time that I had. Okay. So, and then the question is that this only adds one specific limitation, and that limitation is that now I'm telling you that my block offset plus my index should be smaller than page offset. Okay, I cannot have many indexes if it's the number of bits that I need for indexes is larger than my page offset. So for example, if my page offset is 12 bits, my index plus block offset should be less than 12 bits. If it's not, then there will be indices from this side, and this side I cannot use because this is part of the virtual address that needs to be translated. Okay, so it's important that my index and block offset fits into that 12. It could be less than 12, but it cannot be more than 12. And actually, if you think about how we are actually come up with this number, this means that my cache size should be less than the page size time associativity. Okay, and in order to understand why this is, I'm gonna let you guys think about it. And if somebody actually can break it down and prove why this is the case, you can put it on the campus wire. If you couldn't, the TA will actually describe this to you in the discussion session. Yeah. Yes, the question is what the tag is in this situation. So if you remember in my caches, what I had before was, so the cache was like a design like this, that the index comes, we bring the tag, and then we had the data, right? And if this was a set associative cache, then we have multiple of this, like we have multiple independent ways, right? So in order to know which row to select, we use that index, right? So the index was basically helping us to select the row, okay? So what we are saying here is that this index can come from the page offset, which doesn't require translation. So we go to the cache, and then we basically go to whatever index that is pointing to, and then bring that cache down, okay? And bring the data down, okay? And then what happens is that once we're bringing this tag down and this data down, simultaneously, I'm doing the translation inside my TLB. And if you remember, inside the TLB, what we had was, let me see. Oops. Way up. Yeah, within TLB, I had something like this, that I had the tag and I have the physical page number. So this is where we're going to bring the tag here. So now I have the actual physical page number. I have the tag. I can compare these two. And if it's a match, it means that the data is in the cache. And then that's where we're gonna like, send the data back to the CPU. Does that make sense? Yeah. Yeah, because you are comparing your physical addresses together, right? So that's what you do. Yeah.
So it's like combining the tag you got with the offset and the CPN, combining them like
Yeah. So again, if you remember, the PPN was the part of the tag, the part of the address that you used as a tag. So your physical page number is really your tag that you stored in the cache. That's why you're comparing these two together, right? Like how did we, if you, again, going back to the address, if you remember, my 32-bit address was block offset, index, and whatever remains was the tag, right? So this was the tag. So now I'm telling you that if these two parts is my block offset and index, whatever remains is going to be my tag. So I'm going to compare that tag with the tag that I stored in the cache. Right? Yeah. The question is, do we index through the TLB or should we check the entire TLB to see if it's a match? It depends on how do we design. As I said, it's usually we design as a fully associative, which means that you have to step through the entire TLB. The associativity is number of ways, yes. All right, so that's it with the virtually indexed physically tagged designs. Of course, if you have questions, let us know. And then, of course, not every device has virtual addresses. There are many, many systems that are just operate with physical addresses from the beginning, okay? So these things of address translation only happens in high-end processors, okay? In low-end processors, you have all physical address, everything is physical. You don't need address translation and all those things, okay? So if your device doesn't have an MMU or doesn't have an operating system, none of these things actually matter, okay? You just use cache, you just main memory, and that's it, okay? Okay, so let's have a quick break, then come back and we can talk a little bit about the I/O as well. Okay. Okay. So we kind of talk about processors, we talked about memory. Let's also talk about other things, especially like, you know, inputs and outputs, the I/O. So essentially the structure of your system kind of looks like something like this, that you will have your CPUs, okay, and directly connected to your CPUs is your cache, okay. Then we have what we call a memory bus, which basically connects your caches to your DRAM. Then you have a whole bunch of other things, all I/O devices like your you know, sensors and actuators, your Wi-Fi, your network, and all those things. The way that this is connected to your system is through the kind of the what we call the same kind of bus that we have. The bus, you can think about it as kind of connection, that all of these elements are kind of sit next to each other and connected to this. And we usually have this kind of like, you know, component that kind of orchestrate this communication and this connection, which we usually call it a bridge, okay? So all of my I/O devices, it can technically just connect to this I/O bus, okay? And this I/O bus is kind of connected with the memory bus and then connected to the cache and then to the CPU, okay? We usually, the reason that I'm showing this kind of part in blue is we usually have a dedicated bus between the memory and the caches because that's the one that we use very often. The rest is kind of like shared together. So all of your I/O devices typically share the same bus. We have different I/Os depending on the class of device that we are dealing with. So for PCs, for servers, for mobiles, for embedded systems. These are all computers. They all have CPUs and memory and caches and so on. But the I/O that we connect to each one is very different, right? So for your PC, very rarely you actually have many I/Os. You usually just have your network card and maybe your like, cameras and stuff like that. But if you think about something like a Raspberry Pi, you might have actually a lot of I/Os, right? So lots of things that you might connect it to it. Examples are, secondary, ternary storage units. So your disk is usually actually connected as an I/O, okay? You have your network cards like Ethernet, Wi-Fi, Bluetooth, LTE, whatever you have. You have the human machine interfaces such as the keyboard, the mouse, the touch screen, audio, video, whatever else you have. You have like things like printers that obviously need these days, nobody use. Then you have a bunch of different sensors and actuators. Sensors could be GPS, the heart rate, IMUs, et cetera. And then actuators are any sort of actuator that connect to your system, motors, robots, stuff like that, right? So all of them are essentially just a device that is connected to your I/O bus, okay? So how do we actually read and write to these I/Os? What's the connection between the CPU and these I/Os, okay? We usually have two possibilities when we are talking about the connection between my CPU and these I/Os. You either have a dedicated registers or dedicated connections, okay? So you dedicate specific register and say that, okay, register, I don't know, X something something like X100 is connected to this particular I/O. I don't know, for my, it's connected to these pins in my board, right? So having this dedicated channel then means that if I change anything in the I/O, that directly translates into changing the variables and values inside this register. And we know how to deal with registers, right? We talked about how do we deal with registers. We can do the various, so we can directly kind of add this into our ISA and then live with it, okay? That's a very straightforward things, but this is very, very expensive. This is not scalable. We cannot do this for every single I/O that we have in our systems, right? We cannot have like a dedicated pins because the number of pins that I have on my CPU is limited, and this is not scalable, okay? But for some of them, we do have these, okay? The second approach, which is kind of the common approach, is what we call memory mapped I/O, okay? And what does this mean? It means that we kind of treat I/O as memory, okay? And what we do is that we say that, okay, remember I told you that memory has this kind of addresses. Let's actually think that I/O is part of my memory and basically say that addresses from here to here is really just address accessing that I/O. And then if I add more I/O, essentially what I do is that I'm adding more addresses to my memory, okay? In other words, reading and writing to my I/O is the equivalent of reading or writing to my memory. So I use the same load and store. All those things that I talked about memory happens exactly for the I/Os as well. The addresses, the address translation, you can even cache them if you want to, and so on and so forth, okay? So this is kind of like what we deal with in most of our systems. We use this thing called memory mapped I/O that typically handles by, again, the operating system. The operating system tells where these addresses are. And that's why, for example, if you're adding a new I/O, you need to kind of install the drivers and tell your processor where these addresses are. But after that, reading and writing to a particular I/O is as if that you are loading or storing to a particular address in the memory, okay? That's very straightforward, okay? And then, you're still using page table for address translation, but many of them, you don't really need to cache them. The reason that you don't really cache I/O is that I/O, in general, is something that's dynamically changed, right? So you stream data, or you stream data in or stream data out. So you're really not using locality in most cases, right? But you can cache them if you really need to, okay? So in order to kind of like, as I said, so this is kind of like, any questions from the memory map I/O? You're good? If you remember, I told you that this is kind of like what we do for the I/O bus. this I/O bus itself is usually not just one bus, it's usually multiple. And the way that this works is that we have different technologies and protocols. So we kind of combine these different technologies. So for example, we have slower and shared kind of communication. This is usually what we call PCIe or IDE. We have shared but fast communication protocols such as Ethernet or SATA. And then we have dedicated channels, which we usually like things like PCIe is kind of like, examples of that. And then the way that these things are kind of like sharing the same lines or same bus is that they kind of, doing some form of asynchronous protocols, some form of handshaking. So the way this works is that if this is my bus and these are kind of components, since they're kind of sharing the same bus, usually there is this kind of bridge or arbiter somewhere here. So this is the arbiter. The way that this works is that, for example, if this IO wants to write something, they first announce that I want to write something, and this arbiter is basically give them permission to, now you can write. So everybody else has to stay silent. This particular component has to write. And then the arbiter is basically forwarding this data to the CPU or to the memory, depending on how you want to write this. And then once it's done, it tells the arbiter that I'm done. So the arbiter now tells the others that if you have any data, you can actually kind of write it to the bus. And then CPU is the same thing. If I want to write something to the IO, the CPU tells the arbiter that I want to write something to this particular IO. The arbiter basically tells everybody else to stay silent. Then it allows the CPU to kind of write this. So everything is kind of in this asynchronous format of some form of what we call handshaking protocol. That somebody says, I want to do something. Somebody who's the manager or the arbiter tells that whether you're allowed to or not. If they're not allowed, they have to waiting for some other things to finish, and then they're going to continue. So this is kind of like usually the handshaking protocols that we do. I specifically don't go through this because it's less relevant to the computer architecture part of things, but probably might see it in some other courses or you may not. But if you're interested, you can definitely read more about these different protocols of how these protocols are working, like what is PCIe, what is PCI, what is SATA, what is Ethernet, and so on and so forth. Okay. One important thing that I want to mention is this notion of DMA or direct memory access. Okay. So what is a direct memory access and why is it important? So I told you that I have my CPU here, and I have my memory here, and then I have my kind of like, controller here, and then I might have my bus here, okay? So one thing that we can do in order to write things into the system, if this IO wants to write something, it tells this arbiter, and this arbiter can kind of tell the CPU that, okay, something is coming, and you kind of handle the addresses and where this data has to be stored or not, okay? So that's one thing that we can do. The problem with this approach is twofold. One is we keep the CPU busy during this time because whatever we want to write from the IO, I need to ask the CPU, okay, what is the address? Every address needs to be translated. Every address needs to update kind of the memory and so on and so forth, okay? So I keep the CPU busy, and I also do this unnecessary continuous translation because I need to go from virtual to physical back to virtual because CPU only understands things, physical back to virtual, back to physical, right? Because CPU understands things in the virtual domain because it's software, but these addresses are really physical addresses. So there's this unnecessary translation. Again, I'm keeping my MMU and my bandwidth busy. So what I can do instead is that I can have this additional unit called DMA, which is kind of usually sits here. And basically it's looking like this, that if this IO wants to stream a lot of data, it wants to send a lot of data, what we can do is that this arbiter can talk to the memory and basically just write things directly into the memory, into the disk or into the DRAM without the involvement of the CPU. So CPU has no idea of these things are happening. Maybe just at the beginning, the arbiter tells the CPU that, oh, there is this package going to come. and then the CPU gonna tell the DMA to handle it. But afterwards, this thing that basically happens in the background through this DMA. We call this direct memory access, DMA, which means that the iOS has access directly to the memory for reading and writing things, okay? And this significantly helps the CPU because the CPU does not need to be involved. And as a result, no address translation also needs to be involved. Everything can stay at the physical level addressing, okay? So DMA is a very important components that actually have, available in most of our devices. So kind of like, again, summarize of what DMA does. DMA engines offload CPU by autonomously, transferring data between the IO and the main memory. The only thing that CPU knows is that the CPU is notified from the beginning and end of this transaction. Doesn't know anything that happens in between. And then DMAs, of course, can be programmed through this memory map registers. And then we can have the direct communication between the DMA and processors through some registers as well. So if the CPU wants to configure the DMA, it basically writes the configuration into some specific registers, okay? So this is kind of the updated format of our design. So our modern IOs just kind of looks more like this, that you have your CPU, you have your caches, you have your DRAM, and then you have your buses. Then you have your DMA here with these buses that can actually directly write things to the DRAM. And then you have a bunch of different buses. So you don't have just one bus, you have multiple buses. You have Ethernet, you have PCIe, you have SATA, so on and so forth. The way it works is that you usually have some form of bridges between. So you have one IO bridge, and then you have other bridges that connects this faster to this slower. And then you can continue having that. You can have multiple, and whenever you want to add another one, you need to add another bridge, and then you have another bus, and so on and so forth. So you can actually scale this to infinity if you want to, really, okay? And then, for example, if you have other components in your system, let's say you have a GPU, the way that this GPU is connected to your system is exactly the same thing. So you either can have a dedicated line between your CPU and your GPU, or your GPU can basically just sit as one component in your IO system. The reason that we typically go with this format is GPUs needs to be very fast and needs a very fast communication. So that's why you usually don't want to share it with anything else, okay? So you have like a dedicated one-to-one connection between your GPU and your CPU, but nothing prevents you of having a GPU, something like this here as well, okay? Any questions? So the reason that I'm showing it here is that basically DMA is kind of part of this bus bridge. And then as you can see, some of the devices can have DMA, some of the devices may not. So it's not like all the devices have support for DMA. So the last thing I want to talk about the IOs is, okay, now I have data from IO. How do I even notify the processor that I have something to send or receive, right? I told you that there is a protocol, the handshaking protocol. But for example, imagine that your PC is running some, application. You do PC+4. How do you even stop that to kind of, do something else, okay? So there are two mechanisms for this. You probably have seen it and know this. There's polling and there's interrupt. So usually the way this works is that the CPU can occasionally stop executing, its instructions and change the PC to some other PC that's kind of checks whether there is anything that any of these IOs wants to send. We call this a polling-based system, that we keep polling and checking whether there is an available thing for us to process. The other way to do this is that we don't bother the CPU with stopping. We let the CPU kind of go through the instruction memory. Then we have this notion of interrupt, which essentially has higher priority than executing things, okay? So what does that mean is that interrupt, think about it as a branch, which essentially all it does is that if you insert an interrupt, your PC will change from PC+4 to somewhere else in the program memory, which basically is what we call interrupt service routine, which is kind of, think about it as a program that handles the interrupt, okay? So if the new data comes, the IO actually raise an interrupt, the operating system usually catch this and force the CPU to jump to somewhere else in the program and start handling that interrupt, essentially executing the program related to handling that interrupt. Once it's kind of received that data and that interrupt is done, it jumps back to where it was and then continue execution of the instruction. So in terms of the PC and the way that the CPU operates, literally nothing changes other than the PC really just jumps into somewhere else. We're still executing instructions one by one, out of order, etc., etc. The only thing that happens is that if the data comes, we need to change the PC to go and run the program that is associated with handling that interrupt. Okay. The good thing about interrupt is that, there is no CPU overhead until it actually happens. So the CPU does not need to stop executing useful instructions unless there's something that needs the CPU's attention. The problem with this is that this could be at unexpected or unwanted times, and the context switch could be that there could be large overhead for the context switch because the CPU essentially might be in the middle of doing something. It has to stop that and then has to service the service handler, the interrupt handler, versus the polling one is more of like whenever CPU thinks that it's now a good time, they can go and check it. So that's the kind of the difference between the polling and the interrupt. So the good thing about polling is that it can be fully scheduled, but there is also unwanted CPU overhead because the CPU has to stop its execution, has to go through the polling and check and come back. And many times this checking might be, useless because there might not be any data. So what do we do to kind of like, balance between these two? We usually do this hybrid approach where the idea is that the first time we use polling, for the first time we use interrupts. So for example, we don't check whether this particular IO has something to tell us. We just continue doing that. We just tell them whenever you have something, just interrupt us, okay? But afterwards, for example, knowing that this IO going to continuously send us data, we're going to say, okay, for now, don't send us any interrupt anymore. Whenever we have time, we're going to come back and help you, right? So this is kind of like the format that we usually follow in systems in order to kind of find the balance between interrupts and polling. Speaking of interrupts, so let me quickly talk about the differences between exception traps and interrupts. You probably have heard these terms. So let's actually talk about them. So exception is kind of like a conceptual thing. So exception is like when an unusual thing happens during the execution of the CPU, okay? So for example, like, divided by 0, page faults, data is not accessible, you're trying to access some part of the memory that you're not supposed to. These are all exceptions, okay? The exception is just an event, okay? If an exception happens, in order to respond to that exception, we usually, execute what we call a trap, okay? So the trap is what we call, what trap is basically this synchronous transfer of the control to some handler, okay? So as I said before, consider this is your instruction memory, and then you kind of do this, and this is your PC, that you kind of like, read this, and then PC plus 4, PC plus 4, PC plus 4. At some point, something bad happens. In order to handle that, your system traps your CPU to run that. The traps means that instead of running this instruction, go and jump to wherever this handler is, okay? So we are forcing this PC to update its value to some value that we want for it to be, okay? So if I actually want to show this in terms of the design, it will look like something like this. Remember that I had my PC here, and I had some form of a multiplexer that tells me whether this is PC plus 4 or whether this is the target address, like branch etc., right? Yeah, I had something like this, right? So what I can do is that I can add another line here, and that's the kind of the trap line. And all I need to do is that I have a control signal here that forces the PC to get that trap address instead of the actual PC+4 address, okay? In other words, once I do this, next cycle, I'm guaranteeing that I'm running this trap instead of running the actual PC+4 or PC+ offset or whatever I had, okay? This is how we force the CPU to run what I want, okay? And this means that now I can handle various different interrupts or exceptions, okay? Yeah, and then the difference between trap and interrupt is that interrupt are these external events that happens to the CPU. So the trap is something that we usually internally cause it, but if the external things happens to the CPU, we create an interrupt. And then if there is an interrupt, there is an exception interrupt happens. So we technically call an interrupt some form of an exception. And I told you that in order to handle exceptions, we need to have a trap. So the trap is basically go and handle that exception. For the particular interrupt, we call the interrupt service handler or ISR in order to handle the interrupt exceptions. Okay. So just to summarize, exceptions are these unusual events. You can think about interrupt as some form of an exception. In order to handle the exceptions, you have this mechanism called trap, which essentially all it does is changing your PC to the address of the beginning of that trap handler. And all we do is that whenever something happens for our CPU for our execution, all we need to do is that forcing the CPU to jump to that part of the program. And inside there, we kind of handles this. Okay. And I think most of you have done some form of have written some interrupt service handlers. How many of you have seen interrupt service handler before? Oh, some of you. Okay. So you're kind of familiar with it. At least some of you are familiar with it. Some exemption, some examples. So for example, we have branch misprediction, and branch misprediction is some form of an exception, right? And the way we handles that is we flush the ROB and reservation station and all those things. We usually call this a precise exception because we need to kind of keep track of previous steps, right? So we need to have some memory of how my system looked like before this. So I need to recover it to some previous state, okay? We usually call that a precise exception. But if, for example, there is an I/O, there is some data that needs to be sent to the CPU, this is also an exception. But this is not a precise one because we don't need to recover anything. We just need to execute a trap and then handles and receives that data. Okay, so that's the difference between those two. And of course, there is the notion of priority. And the priority means that not necessarily if there is an interrupt, we're going to stop the execution of the processor. If the priority is higher than what we have, then we're going to execute it. Otherwise, we're going to wait until some time and then execute it. Okay. The reason that I'm not really going through this kind of details of this is that these are mostly just relevant to any sort of real-time or operating system course that you take. But since it's relevant to the way that we're designing our computer architecture systems, I wanted to quickly talk about them. And lastly, your system call is actually also kind of a trap, right? So again, for example, your printf or scanf, cout, cin, all of these kind of system calls that you have, they're essentially just traps. They just create a branch and jumps into somewhere else in your program. And that somewhere else is where you handle, for example, printf and cin and cout and all those things, okay? So in other words, all the things that the operating system does translate into just a simple trap. And as far as we can handle the traps, we are good to go. We can connect my CPU to my operating system and to my IOs, okay? This is basically the connection between all the things that you've learned with all these other abstraction layers that you kind of either already learn or will learn or never learn. I don't know. Okay, so this is kind of the big picture. Okay. There's also other exceptions, including, for example, there is a hardware failure. If your device kind of like heats up, what will happen? There There might be overflow. This is another exception, and so on and so forth. Okay. So this is kind of like the big picture of your entire system. So this is, for example, an SoC. What you can see here is that you have things such as, various different ARM cores. You have a bunch of different accelerators. You have different types of ARM cores, actually. Some more performant ARM cores, some less performant ARM cores. The difference between them is, for example, this one, maybe it's an out of order, the other one might be in order, and so on. Then you have your caches, you have your memory managers, you have your L3 caches, and then you have all sorts of IOs that kind of sits next to these. And this is where you're going to have this peripherals to kind of like handle all of these. And you can see there are a whole bunch of different IOs for a device like a macro controllers. You might have many different things. They can have keypads, you can have networks, you can have USBs, etc., etc. So now you can actually have a full understanding of every single component in here. Actually, you should be able to understand how the process works when you have all of these things. Okay. So where are we? We are here. Okay, so we are kind of like where we had the memory wall, and I kind of, pivot and start talking about memory and say, how do we fix the memory wall problem? But then if you remember, I told you that at some point we hit power wall, which means that we can no longer add more features to a single CPU. And as a result, we can no longer make our CPUs faster. Okay. So for the rest of this class, we're going to talk about this rest of this kind of timeline, where instead of like improving our single cores, now we are adding more cores. So we're going to start talking about what we call multi-core system. And then we eventually going to get to this high-end, very like, server level class systems that has many cores and has GPUs and CPUs and so on and so forth. Okay. So I'm going to skip these things and I'm going to talk about this later. Let me just jump into the quiz. So the quiz is going to be about whatever we discuss after quiz 1, right? So this is the beginning of your branch predictor, control flow hazards, the BTB, and dynamic branch predictor, BHDs. I think your homework 4 could be a good example of the type of questions that we might ask from you in the quiz. Then, of course, the whole thing's about out of order execution, different units, why we're putting those units in the system, the example that we gave you, and different things that happens to your RAT, to your functional units, reservation station, ROBs, and so on. And then, of course, all the things that we discussed in the caches, right? Why we have caches, the different structures, hit time, miss rate, miss penalty, all those optimizations that we talked about. How do we reduce miss penalty? How do we reduce miss rate, and all those things? And of course, anything that we said this week that's not part of your, that's not going to be part of your for your quiz. So things about virtual address, page tables, they are not part of your quiz 2. Okay. The format will be the same next week, Tuesday in the class. Yeah. Any questions about the format or anything like that? All right. So see you guys next week.